If you were trying to cure cancer, where would we even begin? Here's a little snowflake. What if I told you that analyzing the secrets of this snowflake could put scientists one step closer to curing cancer? This snowflake is an example of something scientists call a fractal. That means that it has an infinite regression structure, which gives it unique properties. One of those properties is that the regression structure actually messes with the dimensionality of the snowflake. Let me explain by talking about some basic objects and their dimensionality. Let's start with a one-dimensional piece of string. When I use this 4-inch ruler to measure that 12-inch piece of string, it fits a total of 3 times on the string. Now, let's use a 12 by 12 piece of paper. When I use this 4-inch piece of paper to measure the 12-inch piece of paper, it fits a total of 9 times on the paper. Now, let's use a 12 by 12 by 12 cardboard box. When I use this 4 by 4 cube to measure the cardboard box, it fits a total of 27 times on the box. To express this with exponents, we might say, well, 3 to the power of 1 is 3, 3 to the power of 2 is 9, and 3 to the power of 3 is 27. So each time I add 1 to the list of dimensions, I also add 1 to the list of exponents. Let's try this same method on the snowflake I showed you earlier. It's a special snowflake called the Koch snowflake, and it was discovered way back in 1906. When I use this 4-inch line to measure a 12-inch portion of the Koch snowflake, it fits not 3 times, but 4 times on a 12-inch portion. Even if I zoom in, the 4-inch line will always fit 4 times on a 12-inch portion. So let's do the math. 3 to the power of approximately 1.26 is 4. So are we to conclude that a Koch snowflake is 1.26 dimensional? That would be strange. Strange, but true. Infinite regressions are so spooky that they mess with the most basic aspects of shapes, the very dimensionality of them. Fractals are all around us. Many flowers, some ferns, even the cells in a human body exhibit fractal patterns. But what's most important about fractal dimensions is their potential to help scientists cure cancer. That's because cells naturally have fractional dimensions, and cancer cells exhibit more fractal patterns than normal cells. This is the structure of blood vessels in a normal eye. This is the structure of blood vessels in a cancerous eye. You may be able to intuitively tell the difference between them, since the cancerous eye is much more irregular and misshapen. But scientists need some way to boil down that intuition into a quantitative formula that computers can use. And we have just learned how. By analyzing the dimensionality of the patient's eye, computers are able to detect the number of fractal patterns present in the eye, and thereby determine whether or not the cell is cancerous by determining if there are too many fractal patterns. This is one important step on the quest to curing cancer. Thanks for watching.